All right, so welcome. This is a talk put on by IRIS, which stands for Integrating Research in Science. And IRIS is a student-run STEM research conference that occurs in the spring. So in the fall, we're doing these research talks both here and at Elon. So this month is here at Wake Forest, and Dr. Hill is going to be giving it. So Dr. Hill got her PhD from Northwestern, and her research interests are in applied dynamical systems, specifically climate and social dynamics. So, thank you.
Thanks for having me. Okay, so this is like a small group, so I'm hoping maybe we can have some fun. So I'm not going to talk about too much of the math, but about this model, but I do want to give a sense of the big picture ideas and the modeling process and kind of what is the typical modeling approach in applied dynamical systems right now. So this particular topic is about, oh no, the pointer doesn't work on the screen.
Oh yeah, it's not that hard.
No, I'll just point, I guess. Old fashioned. So I'm going to talk about this, which is, so this data set is math and statistics. This is the NSF data about the fraction of the field that is women. So it goes from 0 to 1. As you can tell, it's all below 50%. The colors are going from top to bottom. The bachelor's level fraction, the fraction of graduate students, the fraction of tenure track faculty is higher than the fraction of postdocs, and then the fraction of tenured faculty. As you can see, there's not a lot of change since 1995. And so there's some improvement in the tenured faculty, and in the tenure track faculty, there's actually a slight decrease in undergrads. And so there's a lot of things that people say about gender and other people that are underrepresented in math and any field in particular about why people might leave, why people might stay, and how we can predict, the keyword being predict, the time and how to make people stay when they want to stay, right? So that's kind of what this model was trying to get at. Going the wrong direction. Okay, so before I start talking about the model, I should mention who I am, although everybody in this room knows who I am. But one thing that I found most useful in these kinds of talks that I went to when I was a student was people talking about their mathematical stories. Not necessarily their stories of their mathematical journey, but their stories of their journey as a mathematical person. So I'm going to mention my talk, or I'm going to mention my journey just so you have another data point of somebody's story, also as a woman in math. So I'm also going to mention what is a dynamical system. Based on the people in the room, I might go through this rather quickly, because I think you all know what a dynamical system is. And then I'll talk about the model. We'll spend the most time in the model. Okay, so Sarah Ruth basically said all you need to know about me. But here's some more stuff. I was born in San Antonio. And then here's a list of things that I typically talk about on my CV. I went to Baylor, so that's the first 5 things. And these are also kind of items that you should feel free to ask me about or talk to me about at any time in case you're interested in doing any of these things. So I did 2 REUs and a senior thesis. I got my bachelor's degree not in math, but in a liberal arts kind of degree where I was required to read a significant portion of what they call the great texts. As part of that, I could choose a concentration, and my main concentration was math, don't worry. But my BA was actually in something called University Scholars. to graduate school, I went straight to a PhD program. I got the NSF GRFP in my second year, and then I did my dissertation on Arctic energy balance models. I've done 2 postdocs so far. My first postdoc was ironically at an R1 institution, but it was a teaching-focused postdoc. My second postdoc is ironically not at an R1 institution, but I think of as my research postdoc. And I'm at my second one right now, Wake Forest. As you can tell, I color-coded these. Yay. So this is like the thing, the information you can get from my CV. So why would I bother talking about that? Is because I think it's really useful to hear the stuff that doesn't go on the CVs. So like, for example, also I wrote some papers. So if you want to talk about like writing papers, I have some papers we can talk about. Like LaTeX, like grammar. I really like grammar. I'm always happy to read a paper for grammar. It makes me happy. Yeah, so, but things that don't go on CVs are love. I met the love of my life in freshman year of college. And they lucky for me, they followed me throughout my journey, which is typically a hard thing to do, or hard to have people with careers traveling together. I met the second love of my life last December, which is my baby Elliot. I will happily share pictures galore with anybody that ever asks. Other things that it doesn't talk about is negatives, right? So bad things happen in everybody's life. I had some significantly bad things happen in my life when I was very young, and then maybe more impactfully during graduate school, where I reached such a low point that I almost dropped out of graduate school. And in fact, probably the only reason I stayed in was because I managed to reach out for help. And as a result, I've begun a journey of positive mental health. That's like a healthy brain, right? So if you ever want to talk about mental health, I am more than willing and happy to talk about it. I think it's an important thing that we don't talk about enough. Yeah, we also don't talk about our failures, right? So this is my mathematical path, but what I didn't talk about is the fact that I went into college trying to become a doctor, and that path didn't work out. Thankfully for me, it didn't work out rather quickly. I talked about getting the NSF GRFP. What I didn't tell you is that I applied for several national scholarships before that one and didn't get them. I applied for the Goldwater, didn't even make it past the college level. The Truman Scholarship you might not have heard about because it's more of a policy-oriented national program. It's kind of like on the same level as Marshall and Rhodes. I got a little further in that one, made it to the final 6 out of, they choose 2, and I made it to the final 6 from Texas. But still, no cookie, so try it again, right? The moral of the story is you see everybody's success on their CV, but you don't see the fact that they had to maybe try more than once to get to that success. Okay, so that's my story. Let's talk about dynamical systems. So, pop quiz. How would you solve this differential equation? I'll take younger by mathematical metrics answers first, and then we'll call on Dr. Ross. No, you don't have to. Anybody? Yes?
I'm moving y variable to one side and dt to another side.
Yeah, separation of variables. I agree wholeheartedly. This one is actually a particularly nasty one, although it doesn't immediately look like it, right? Envision solving the integral of y squared minus 1 over y squared minus 1, integrating that and then solving for y. Right? Not actually very fun, but I want us to think about the solutions, whatever they are. Suppose we like did all that work. It was a bad homework problem. Suppose we find those solutions. When I say the word dynamical system, all I mean is an ODE, right? But it's an ODE where we care not just about the solutions, but but their behavior as time goes to infinity. And as it changes with parameters. So I'm going to introduce the parameters alpha and beta. In our previous slides, alpha was -1 and beta was 1. But suppose we let these change. Dynamical systems, in the field of dynamical systems, looks at the behavior of solutions in the long time limit as parameters change. And it gives us a sense of what is the ultimate behavior of a dynamical system or a mathematical model. So in particular, we can look at how the right-hand side of the differential equation varies with parameters. Say for alpha equals -1, we see we have two intersections, 2 points where dy dt is 0. What's the importance of those values? Anybody? We just talked about this in modeling. What is this point? If I put f in the vertical axis instead, would that be more intuitive? Maybe it's Friday. Those are the fixed points. That's where the fixed points exist. Okay, so one of them is positive, one of them is stable, and one of them is unstable. And we might vary alpha and see how the right-hand side changes, and see as we move, we lose our roots, which means we lose our fixed points by the time alpha gets to 1. So when alpha is 1, that's what the solution looks like, and we can think of solutions as kind of varying along this axis. If I kind of turned that picture on its side, if I rotated it, and drew the axis as this line instead, we can see that when we change alpha, these vertical lines kind of like start shifting to the left, right? And if I were to make alpha its own axis and put y as the y-axis, then we can make a bunch of vertical lines and stack them on each other, stack them next to each other, and then we'll get something we call a bifurcation diagram. This type of bifurcation in particular is called a fold bifurcation. So you can see it kind of looks like it's folding in on itself. Folding in on itself. There's other possible types of bifurcations based on how the right-hand side of our equation varies with the parameter. Some cool words are transcritical pitchfork, which looks actually like a pitchfork. I also have something called period doubling bifurcation up here, which is not actually in continuous time differential equations, but in discrete time. And this is where you might have seen the word that is most often associated with dynamical systems, which is chaos. Right? So chaos theory is another word for dynamical systems. Okay, so now I'm going to talk about this model. But I say in kind of like retrospect, I should not say I, because there are many people who should be at the front of the room with me. I've been collaborating on this project and some follow-up projects with several people. So I'd like to thank them beforehand. So what is this model about? This model is about this triangle. Right, so it is a fact that women make up about 45% of the workforce. And this percent goes down as you go up the corporate ladder. Right? CEOs, women are 5%. That is certainly less than 45%. So a natural question to ask is why? Right? And this is one of those very hard kind of questions that's also very simple to ask, but it's a very hard question. So this snapshot is from 2019, but you might say like, oh, well, things have been improving in recent years. In 2020, McKinsey did an analysis that said ultimately, not really. Well, in the past 5 years. If we think longer back, that this is actually improving. But so this one, we've kind of turned that triangle, that pyramid over on its side and looked at, so the A column is the entry level and the F column is the C-suite level. Yeah, so it's not improving over time really. And this is true in many different industries. So business is definitely is one of the most studied industries where this is occurring. It's also occurring in medicine, law, politics, academia, and journalism and entertainment, believe it or not, also has a bit of a hierarchy, and you can also see it in there. So what my collaborators and I did was we looked at a bunch of different fields and gathered data about them. So this is kind of one of the, if you're ever interested in what the fraction of women is over time in a bunch of different fields, you can look at the data in this paper. So this is what math and statistics looks like. You already see all this picture. Journalism, like I said, is also hierarchical a little bit. There are traditionally fewer steps up the hierarchy, but it definitely has an ordering. Computer science is kind of wiggly, which I always think is really interesting. Computer science oscillates a little bit. Nursing is pretty straight hierarchical, but in the other direction, right? Nursing is a majority women field, and it's improving slowly but surely over time. Academic medicine is one of the strongest improvements, actually, from 1960 to 2020. So, in my modeling class, I always say we have to define the modeling question. What is the modeling question? So my collaborators and I kind of came up with 3 questions. One is, what's going to happen, right? What's going to happen to the fraction of women? The second modeling question was, what are the important sociological factors to explain what is currently happening and what has happened in the past for the fraction of women in a field? And not in the least, third but not least, what kind of interventions could lead a field to become more equal faster? Okay, so our hypotheses, our hypotheses were that there were 2 main factors. We're kind of like sick of the leaky pipeline way of talking about people leaving a field, that they somehow have no self-interest and they're just somehow falling out. But sometimes people choose to leave, right? So we wanted to put into our model some sort of self-determination. So at the same time, so that's why we said that, well, a person has to decide to seek a promotion, right? So that we said was affected by something called homophily, which is the tendency to go towards a group of people that you can see yourself in. It's like a self-seeking kind of behavior. It's not specific to gender. So the idea is that people have a certain fraction of gender that they would see themselves best in. Not necessarily 100%, not necessarily 50%, but that there is some optimal gender distribution that people like to see. The second factor is that they have to be chosen, right? You apply for a job and then you're chosen for the job. And then we said that when all other things are equal, when you have 2 completely identical candidates and one over the other is chosen based on gender, we call that a bias, or gender-based bias. So these are our 2 hypotheses, that these are the 2 main things at play in this model. Yeah, so here's like a picture. So we said that, oh, I keep wanting to point. We said that you'd be more likely to seek a promotion if the fraction of women in the higher level matched the fraction of women in your current level. Okay, so an example promotion process is that because of homophily, women will choose, and the flip side, right, men will also choose to apply for a promotion. And then because of bias, a certain percentage of them will be chosen for that promotion. So here are the equations of the model. So you can see this is in the lowest level. We have a general population and an initial hire that happens at some rate. At that level, some people will leave the field and some people will be promoted. To the next level, where you have again people coming in, some people leaving, and some people being promoted. You can do this for as many levels as you want to make. In the pictures that I'll show in the rest of the project, we have pictures showing 3 levels. So at the last level, you have people being promoted, and there's nowhere up to go from this. So the only option is to leave, but in this top level we call it retirement. Yeah. Okay, so not talking about any of the math. Here's what simulation results give us when there's no bias. So when there's no bias, we have that if there's no homophily, like people don't care so much about what the fractions of gender are like, things go to equal gender pretty quickly. On the other hand, if there is high homophily, things will go to the state of the system, so the fraction at the different levels goes to either a very male-dominated state or a very female-dominated state, depending on initial conditions. And in between there, we have spaghetti. So this is oscillations. We call this limit cycles. And the effect of bias is a little bit complex and a little hard to untangle, but easiest to see in terms of the extremes. So when you have no homophily, when people don't care about the levels, bias means that in subsequently higher levels, fewer women will be hired. In high homophily beats bias. So it is similar behavior. And moderate homophily kind of acts the same as no homophily, and then it pushes down. Like instead of oscillating about the equigender state, we're oscillating about some sort of lower number fraction. So as a way to summarize what kinds of possible behaviors our model does, dynamical systems people generally draw a bifurcation diagram. This is a lot to unpack here, so I'm not going to talk about any of the details, but I want to kind of point out some behaviors. So here we have the same pattern, right, that I showed on the previous slide. So here we have an equigender fixed point for low homophily. For moderate homophily, we have spaghetti, which is limit cycles and oscillations. And for high homophily, we have an isogender fixed point, which is to say a same gender fixed point. So let's zoom out and we can ignore a portion of the graph where complicated things happen, and literally map these plots to the bifurcation diagram. And if we wanted to incorporate a small amount of bias, this bifurcation that was here breaks, and other stuff happens, which is kind of fun. And if we wanted to look at 2 parameters varying, we can do something called, we can make something called the bifurcation curve diagram, where every point that's plotted here is a bifurcation. So the way you can think about it is the picture that I showed on the last slide is a single slice horizontally of this bias parameter. And how we made these diagrams is by something called numerical continuation. And if you're curious about how we did that, feel free to ask me anytime. And as an advertisement, if this is kind of intriguing to you, I suggest you check out the MSc 750 class that Dr. Gemmer will be teaching next spring. Okay, so in the last 2 minutes, last 1 minute maybe, I just want to say briefly that a model is meaningless unless we can connect it to real life, or it has very little meaning. So we fit our model with data, which means to say we tried to see what parameters we could make our model replicate data, and how well did our data replicate it, and what we could say about that. So we fit it, and we took a bunch of different fields and fit them in the bias homophily plane. So you can see things to point out. Here's math and stats. And here's nursing. That's a fun one. That's a data set I found, so I'm always excited about that. Academic engineering is way up here. So like, what does this mean? Like, what do these points mean? The color of the point means the average, like, top level fraction. So 0 means 0 fraction women. 1 means 0 fraction men. So some big takeaways of here is that as we have for fields that are above the 0.5 Markov bias, that means that they indicate a preference for women in those fields. And in the bias less than 0.5, we say that's a bias against women in those fields.
Oh, so that means if like you're a male, let's say you're applying to be like a male nurse, you have an advantage?
Yes.
Oh.
Mostly because they were so few male nurses, and now that they actually are encouraging them, it makes the data look very, very male biased, but it's in fact just because there were so few beforehand. Yeah, so there's some outliers here where the data fit is good, but what does it really mean, right? We have to think about that. Oh, and so we can also talk about intervention strategies. So if you're in academic chemistry, because it suggests a bias against women and a moderate homophily, we might suggest targeting hiring committees, doing things like implicit bias training. Similarly for academic biology, right? Implicit bias training against men might be a good intervention technique. Where you see that there seems to be less bias in a field, but maybe more significant homophily, we might suggest targeting the applicants, encouraging applicants to apply. Engineering practice is one example of those. Medical practice seems to have little bias, little homophily, and eventual parity. So that suggests that perhaps no intervention is necessary. So some future ideas and some stuff I've worked on with some students has been, what if you, instead of treating this like a compartmental model and treating like people as a continuum, what if we have actual individual people and see how individually, if they act randomly, what happens? So I've looked a little bit at an agent-based model. Another option to look at is maybe networks, right? If you have networks of people who you know should have some sort of impact. Haven't looked at that yet. But if this seems interesting to you, I'm always happy to talk about it and talk about it more. So thanks for your time. Any questions? Yeah.
I saw on your bifurcation chart you had like a homoclinic. So is there like a homoclinic bifurcation in this?
Yeah.
Oh, that's cool. Do you know if it's like a Schillner-Cloud bifurcation?
We think it is.
You think it is?
Yeah.
That's cool.
Can we go back to there? You mean?
Yeah, I saw it.
You mean these lines?
I saw it on the next slide.
This one?
It was like, I remember just seeing like a homoclinic orbit was like in green or something.
Yeah,
Yeah.
oh, white crap. Yeah, these are all homoclinic work.
Are they? Oh, okay,
applications.
okay.
Yeah,
Oh, that's
and
cool.
they kind of look like there's some snaking behavior, so it looks like they're showing off.
That's cool. That's
But
cool.
it was getting, so the dynamics of this are definitely not as well explored as they could have been, but it was definitely getting further afield from like, what does this mean for the model?
Right,
So I
right.
decided not to pursue it.
Yeah, yeah.
We're actually looking at it right now.
Oh, that's good.
Me and Avi. Mhm.
When you were trying to fit the data, did you allow for the possibility of different levels of homophily or bias at different levels?
No, we didn't. That is definitely something I want to look at, because it makes a whole lot of sense that there would be. There's so we were using something called the. Let me see if I can get to it real quick. We were doing something called the Nelder-Mead algorithm for our data fitting, which is good to know if you ever. Oh no. It's good to know if you're ever doing any data fitting, people in the room. The Nelder-Mead algorithm basically randomly fits mean squared error between data and your model with several fitting parameters. And there's some best practices in data fitting that says that you have to balance the number of parameters you're fitting with the number of data points you have. And we didn't have enough data points to be able to have more parameters. So we had to let that go, unfortunately, to do the data fitting. But I would be curious to see what.
Do you have like
happens.
intuitions in general about like if there's more or less bias between the like lower level versus the higher levels? Or?
No, I don't have intuition that I'd like to say. I really want to, that'd be cool to look at. Yeah, for
It could be like a feedback loop, right?
sure. Mhm.
Like you feed in, you tend to hire people like yourself, so it's like feeds up, building a bias.
Any questions from the students? Yeah.
So when you were fitting the data, is that specifically at like the entry level or just in general?
All levels.
Okay.
Yeah, so the RJ, NJ, XJ, those are for all, so in the model where we were showing you the data fits, there's a little bit of a lag, sorry. Here. So for each of these data sets, we took however many levels were in the data set. So here there's 5, there's 5 here too. Sometimes there are as little as 3. And we would use, so the data points we would fit were these time series, which are sometimes short and sometimes super long. Like academic chemistry has been keeping track of this stuff since the 60s. But math and stats, 1994. So we would fit the level, yes, the answer is yes. we would fit based on the different levels.
I'm not sure if I understand exactly what homophily means. Does it mean the fraction of people in the next level that are like me? Or does it mean how much the fraction of the people in the next level are like me affect my decision? Okay.
Yeah, so it's a very general, I guess maybe psychological, socio-psychological term that says that people in general like to be among people that they feel they have some similar traits with. Like, I like hanging out with Dr. Gemmer partially because he's a Tolkien fan, and I'm a Tolkien fan too. So this isn't specific to gender, and it has lots of broad applications to race as well, race and chosen field. So at some level, everybody has a certain amount of homophily, like a baseline homophily with the people in their field. Was kind of our inherent assumption, but that maybe other factors of their identities would influence whether or not they still felt welcome or like a part of the community. And so we said, like, well, like as a So for different like identities, we accept that we may be able to be well represented in a field or not well represented in a field. Like as a redhead, I'm okay like being the only redhead in a room. I don't really care. But I do notice when I'm the only woman in a room. And I also notice when there are only women in the room. Like I would prefer there to be a gender mix, personally. And so that's what we kind of operated with, that people preferred some sort of mix that would be optimal. So you could imagine different scenarios where you say like, oh, actually I prefer to be the only person in the room with my characteristics, and see how like that changes things. That certainly would change the dynamics. But it's a very broad phenomenon. Any other thoughts, questions? What do y'all feel about, so, we're out of time, actually. I shouldn't, I just want to talk about this. I always want to talk about this. So feel free to talk about this with me anytime. I'm happy to. Thanks for coming.